Amrut Vyakhyaan. This is the 38th Vyakhyaan of the series of Vyakhyaan of 75, which is being organized as a part of PRL's 75 years of legacy and history in the field of fundamental physics and space sciences. Established in the year 1947 by the father of Indian space program, Dr. Vikram Sarabhai, the PRL's Platinum Jubilee coincides with India's 75 years of independence. Hence, it's a joint celebration of science and technology in India by PRL under the banner of PRL Ka Amrit Vyakhyaan. Today, we have yet another very distinguished speaker, Professor Ravishankara, a distinguished professor at University of Colorado or Colorado State University in the Department of Chemistry and Atmospheric Sciences. And he is going to deliver his talk on the ozone layer, its science, and its policies. This is a very apt topic for today's Vyakhyaan because ozone, as you all know, is a prime species in the atmosphere, which is very important. And we'll listen from him on today's what's happening in this area and what are the policies for future. So I request my colleague, Professor Pallam Raju, to kindly introduce our today's Vyakhyaan Karta, Professor Ravishankara.
Thank you, Dr. Bharadwaj. It's indeed a great pleasure and honor for me to introduce our speaker for today. Dr. Ravishankara is a university distinguished professor in the Department of Chemistry and Atmospheric Science at the Colorado State University. Previously, he was at NOAA as the director of the Chemical Sciences Division at NOAA's Earth System Laboratory in Boulder. He has worked over past 4 decades on the chemistry of the Earth's atmosphere related to stratospheric ozone depletion, climate change, and air quality. His laboratory and Earth's atmospheric measurements have contributed to developing the ozone layer, to deciphering the ozone layer depletion, including ozone hole, quantifying the role of chemically active species on climate, and advancing understanding of pollutants formation, their removal, and their properties. Dr. Ravishankara is a member of the US National Academy of Sciences, a foreign member of the Royal Society London, and a foreign fellow of the Indian National Science Academy. He's also a fellow of the American Geophysical Union, the Royal Society of Chemistry, the American Association for the Advancement of Sciences, and the International Union of Pure and Applied Chemistry. His many awards and recognition include an honorary doctorate degree from the University of York in the UK, Montreal Protocol's Scientific Leadership Award, the Polanyi Medal of the Royal Society of Chemistry, the Stratospheric Ozone Protection Award of the US Environmental Protection Agency, the Silver Medal of the US Department of Commerce, N.A.S. Robertson Memorial Lecture and Medal, and American Chemical Society's Award for the Creative Advances in the Environmental Sciences. He has presented numerous named lectures in many countries. He was the chair of the Board of Atmospheric Science and Climate of the National Academy of Sciences from 2014 to 2021, and a co-chair of the WMO and UNEP Science Assessment Panel on Stratospheric Ozone from 2008 to 2015. He is a member of the Science Advisory Panel of the Climate Clean Air Pollution of UNEP and the chair of the Advisory Committee for the Vienna Convention Trust Fund. He is on the editorial boards of proceedings of National Academy of Sciences and several other journals. He has previously served on many other editorial boards and was the editor of Geophysical Research Letters. He was also co-chair of the Air Quality Research Subcommittees and Interfederal Agencies Committee before leading before leaving NOAA in 2014. He is an author of more than 400 peer-reviewed publications and several data evaluation assessment reports. It is indeed a great honor and a pleasure for me to invite Dr. Ravishankara to please deliver his the PRL Amrut Vyakhyaan on the very pertinent topic and exciting and important topic of the ozone layer, its science and its policies. Thank you. Please, Professor Ravishankara, over to you.
Thank you very much. It's very kind. Really appreciate the introduction and the opportunity to talk to you all. So I know it's 5 o'clock in the evening. So good evening. I'm going to do a little bit of a storytelling. I just thought, given the audience, it will be better to talk about some general issues and tell you the story of the ozone layer and its science and how its policies came about. Whenever I give a talk, I kind of ask myself, why should I give this talk? What qualifies me to give a talk like this? So here are my excuses for giving this talk. I got into this field as a postdoctoral researcher at the very beginning of this field. Then the ozone hole was discovered, and there's a big change in this field. I've been involved in the science of ozone layer since the late 1970s. Then I was fortunate to be involved in the assessment of the ozone layer science, both for United Nations environmental program and for the United States for various activities. And so that gave me an opportunity to interact with policymakers at the international level and also at the national level. So this is my collective experience with this particular field. So before I say anything else, I really should thank all my colleagues whose work I'll show. For the most part, I'll attribute that. And I'm not going to list all the colleagues who did the work because it just takes too long. So this is the story I would like to tell you. I'll start with a very brief history of the ozone layer, how it went from a curiosity-driven science to a global environmental problem, and how, amazingly, this global environmental problem was addressed by the actions of the world in terms of the Montreal Protocol. Montreal Protocol is considered the most successful environmental treaty that we have. It has been ratified by all the countries in the world. It's a universally ratified treaty, unlike many other treaties. Being scientists, I just want to tell you what is the role of scientific assessments in doing this kind of work. You are all familiar with doing the research, and you know why you're doing the research, but you may not be as familiar with how that research is transmitted to the policymakers. So that's the role of assessments I'm going to talk about. Then I'm going to talk about the Montreal Protocol itself. Even though it has been a very successful treaty, it's always worth asking the question, is it doing what it was meant to do? And is it doing it well? What else does it need to do? And then I have a few more thoughts going ahead with as to what the Montreal Protocol can do. So, how did this whole business of ozone layer start? In fact, all of our science, it started with observing our environment, in this particular case, the atmosphere. The picture on the left is a picture from Chandrayaan moon mission, which shows you the Earth. I love this picture. The thing that you notice, of course, is that in that picture, you cannot see the atmosphere. It is so thin that it's just not visible. Now, within that very thin but 100-kilometer, maybe thick layer, of course, it keeps going down. There is one molecule that's of extreme importance, and that is ozone. The ozone, as you know, is an allotrope of oxygen, and it has 3 atoms of oxygen. And its structure and its properties are quite unique, and it's what makes ozone such an important molecule. It is sufficiently weakly bound that it can decompose with sunlight, unlike nitrogen and things of that nature. But it also has this incredible property of absorbing ultraviolet radiation that makes it safe for living creatures on the Earth's surface. Most of the ozone actually is in the upper atmosphere, in the stratosphere, as shown here. This, of course, depends on how you plot this. This is in ozone mole fraction. But of course, ozone is there everywhere. It starts at the ground, and this is a pollutant that we don't want to have. And there is ozone in the troposphere and the upper troposphere, especially where it's a very potent greenhouse gas. And then here's the UV shield that is of interest to us today. So ozone is everywhere, and that's what we want to think about. The history of ozone goes back about 200 years. A chemist named Schonbein discovered ozone, and he called it ozone because in Greek it means smell. If any of you have smelled ozone, it is very pungent, and it smells almost like NO2 if you have smelled that one. And then Cournot from France saw that there's a sharp cutoff in the UV radiation when you look at the solar spectrum. He wasn't sure what it was due to, but then Hartley measured the ozone absorption cross-sections spectrum in the laboratory and showed that what Cournot was seeing was the atmospheric ozone, and they were very clever by looking at the amount of ozone absorption they see as a function of solar zenith angle. They could figure out it is in the stratosphere. And it was a century later, after ozone discovery, that Sidney Chapman explained how the ozone layer works. And his simple current explanation was O2 photolizes to give oxygen atoms, and oxygen atoms react with molecular oxygen to make ozone. If this is all that happened, of course, all the oxygen in the atmosphere would have become ozone. So there must be a counteracting force, and that is because ozone itself photolizes to give oxygen atoms, and oxygen atoms themselves react with ozone to make 2O2, 2 oxygen molecules. So there's a dynamic balance, a delicate balance in the formation of ozone and the destruction of ozone so that you maintain a steady state amount of ozone in the atmosphere. This is a very important point because we are not looking at taking away ozone, it is changing the steady state. That's what is of interest. If any of you are interested in this history, Guy Brasseur has a beautiful book. It's called The Ozone Layer from Discovery to Recovery. I highly recommend it. While this was all going on, a gentleman named Thomas Midgley, who was an engineer, and a chemical engineer actually, and he was working at Thomas Hochwald Laboratories in Dayton, Ohio, and he developed chlorofluorocarbons as refrigerants. Before chlorofluorocarbons, refrigerants were things such as sulfur dioxide and ammonia, which are pretty toxic. To show that these molecules are non-toxic and they do not burn, that they don't explode, what he used to do was to inhale the CFC12 and gently blow on a candle to show it will put out the candle. It didn't make the gas burn, it actually put out the candle, and he was still walking around, and so clearly he showed it was non-toxic. This gentleman was also the discoverer of leaded gasoline to reduce the knock of engines. These were major technological innovations in this era, and in fact, it ushered a huge change in the demographics of the world, especially in North America. But these major innovations had pretty consequential environmental impacts that he unfortunately didn't live to see. Then came along in the 1970s, early 70s, the idea that supersonic aircraft would destroy ozone. This was from Harold Johnston and Paul Crutzen. And the idea here was the nitric oxide coming from aircraft combustion would essentially react with ozone and destroy ozone. And then Stolarsky and Cicerone were looking at what would happen if there are space shuttles. They were originally thinking there could be a space shuttle launch every week. That didn't come to be. And the space shuttle contains ammonium perchlorate, it's a oxidant, and so it produces chlorine. And they were looking at what chlorine would do in the stratosphere. And they figured out there's a chlorine catalyzed ozone destruction. And then, of course, the famous Molina and Rowland discovery was that CFCs could be the major contributor to chlorine in the stratosphere. The key point of this, though, is because these are catalytic cycles, both with nitric oxide and chlorine, a very small amount of chlorine can destroy a very large amount of ozone. So it could affect on a global level. That is the idea. So this catalysis this homogeneous catalysis enabled small amounts to destroy large amounts of ozone. So in those days, we used to do these calculations of what is the projected ozone depletion in 2050, that's 30 years from now, where we thought the CFCs would be as much as 9 parts per billion, and the calculated ozone depletion were small. This is the year in which the calculations were made, and these changes occurred because of measurements of chemical reaction rate coefficients. This is where I got involved in changing some of these values. But the take-home message is what we are predicting was this is going to happen long time from now in 2050. Second, it was not a huge effect, maybe 5 to 10%. And third, it was very uncertain. There's so many things changing this. So there was this feeling that it is something to worry about for the future. And we already knew that the ozone layer depletion would have a harmful effect. So the amount of ozone in the atmosphere is pretty small. If you take all the ozone that's above ground and brought it back to where you are, that ozone layer will be a few millimeters thick. That's all there is between you and the sun in terms of UV protection. And of course, we already knew that surface ozone, UV radiation can hurt biology. For example, this plant was exposed to UV and this one is not exposed to UV, And you can see this is healthier than this one. Then there is effect on food production in this ocean by these little creatures that will be destroyed like krill. And then the big point was this UV radiation can cause cancer. Cancer is a very scary word. That really is what got people thinking about it. While this was going on, there's an amazing development, totally unexpected, and that was this discovery from Joe Foreman and colleagues that the ozone layer over Antarctica in the month of October was way, way depleted compared to the other times. This is a huge phenomenon. And then Susan Solomon came up with the right theory for this ozone layer depletion over Antarctica as being due to chlorofluorocarbons and the catalytic cycles that happen there in an unusual set of circumstances that makes ozone go away much faster in Antarctica during those times. Then there were detection of the global ozone layer depletion at the same time. And lastly, there were measurements done over Antarctica. Huge amounts of experiments were done. And one of the key figures from that is shown here, which says it shows ozone and CLO, which is essentially a marker for the chlorofluorocarbon coming in there. And as you can see, it just clearly shows the anti-correlation that CLO was destroying ozone. So we actually understood amazingly what happens over Antarctica within roughly 5 years of the discovery of the Antarctic ozone hole. It's an amazing set of developments that happened. And that really made this headline news. So for example, this was the cover of the Time magazine showing there's an ozone hole and the vanishing hole. This impressed upon people that what we are doing on Earth can have a global effect, and it's really seen very clearly. So the observed and projected ozone layer depletion from a curiosity-driven science became a societal issue with a societal response. So by 1980s, the massive ozone hole was known, the global ozone layer depletion was detected, and the conclusion was human-made chemicals are depleting the ozone layer. So that led to the Vienna Convention and the Montreal Protocol in 1987. If any of you are interested in this history, there's a paper by Tina Bimpili, which kind of goes over that history. At that point, the world had a choice. They could continue to do what's happening and say we'll do something in the future, or they could take some action. So this is a contrast in question. It's a question of, do you mitigate this effect or do you adopt this effect? So there were people who were saying you can let this thing go, in which case the amount of predicted ozone depleting substances would have been increasing like this in the red line. At which point you'll have to adapt, which means you have to cover yourself and move north and do all sorts of stuff. Or you could mitigate and just get rid of these substances and continue our life as we know it. Okay. Amazingly, the world opted to mitigate through the Montreal Protocol. I mean, then you can compare with other treaties and other environmental issues, especially climate, as to what we are doing. And if you have time, we can talk about it. Okay. Now, how did this come about? One of the key things that came about here was transmission of scientific information to policymakers. And this is the role of assessments. This is the telling people who need to make decisions what science knows and what science doesn't, and what are the possible actions they might be able to take. The science really foreshadowed the Montreal Protocol. The simplest way I can tell you is that the Montreal Protocol, without it, the ozone depleting substances would have been going up exponentially like this. With the Montreal Protocol, all it said was, we won't go up as fast as this. So this it's a deja vu, with climate. But then as science progressed and we found out more and more things, and in various assessments, the amendments of the protocol were made so that there are higher and higher actions to reduce the ODSs to essentially emissions to essentially zero. So these assessments, one after another, showed why it needs to be done, otherwise what the consequences should be, and at the same time, it showed how it could be done. So the advancement in science was a key impetus for policy. So let's delve into this a teeny bit more. How did assessments lead to policy? One of the nicest things the Montreal Protocol did was it institutionalized the assessments. Assessments had to be made every few years, and it had to be reported to the parties to the protocol. And these assessments showed the science and the technology of what is going on and the economics of what is feasible. And then it included not only CFCs, and then it included carbon tat, halogens, and methyl bromide. The technology showed that there are substitutes that you can use. I'll show you in a few minutes. And then the economics was discovered and how elucidated, and people could figure out how things could be done. So this is what I would call baby steps. You took some easy steps, one after another, and it built the community, built the trust, and built the trust between scientists and the policymakers, and it made it happen. So let me just spend a couple of minutes on what is a science assessment. This is an idea that I essentially stole from my mentor, my former laboratory director, Daniel Albritton, who was an amazing communicator. His idea was simple. You have researchers who do research, and then you have customers for the information. It could be government, industry, or the public. But you need somebody who can translate the research to the customer so that they can understand in clear terms what's happening. He used to call these people the amphibians who could live in two worlds. This is a picture of Escher. So the idea of an assessment is it's a bridging function which connects the findings of the research community with the needs of the customer community. And knowing what the customer community wants, then the science is done by the researcher. It's a two-way street. It's bidirectional, and it bridges these activities. And if you look at the taxonomy of this process, what you have is this scientific underpinning by the peer-reviewed publications. The whole idea is peer-reviewed publications is the gold standard for this. And then you have synthesis of the information from the peer-reviewed this is assessed information. There's technical that can be in chapters. And then you come up with the key scientific points. And then the readers for the chapters are mostly scientists. These are people who can do a little bit more than science. And then finally, there's a science for policymakers or executive summary that can be used by the policymakers. So this whole pyramid is built in such a way, the essence of the scientific information are transmitted to the people who need to make these decisions. The way Montreal Protocol codified this is that in addition to the scientific assessment panel, there was an environmental effects panel and a technology and economic assessment panel. This was particularly important because essentially what this enabled, I have lots of words there, but I'll just tell you what it is it provided the information in user-friendly terms for the user. And it provided viewpoints. It was not reviews. These are expert judgments. And it was one-stop shopping to get all the information you wanted. And especially the synthesis report that synthesized all the information was extremely useful and user-friendly for the policymakers.
Dr. Ravishankara?
Yes.
Sorry to interrupt, but there is something on your monitor screen on the right side. It is covering the text.
Oh,
Yeah, Kiba, please. Yeah.
I don't know how. Okay, let me see.
Yeah, it says something about some reminder, so you will have to dismiss it.
I don't know how to do it. Let's see.
Sorry for the interruption.
Now I don't see a cursor. Oh, there.
Yeah. We see your cursor. It's right now exactly the dismiss. Yes, done it. Yeah, I think that's okay.
No, unfortunately, that's not doing it. That's a reminder that I'm.
Reminder, yes.
Should be getting ready for my class.
Okay. Okay.
Excuse me. I'm going to just get off of this and I'll start over. Sorry. There you go.
Yes, now it's gone.
Okay. Sorry about that.
No,
I should have turned that off. Okay. So there was it. So essentially, this is a key ingredient for continued adaptive decision making. I'll come back to this adaptive decision making concept in a few minutes. A few more words very quickly about assessment. It's not a consensus. It's a consensus, but that doesn't mean everybody has to agree. It is policy. It's not prescriptive of policy. The customers are known before you start. And the whole idea is you just tell them, if you take action A, you'll get outcome B. If you take action B, you'll get outcome B, etc. Essentially, you let the policymakers make policy and you just give them the information. Just a few more words, I'll just skip it. So what came out of this was this unwritten but understood strategy that you'd phase out chlorofluorocarbons. In the first part, when you're phasing out the chlorofluorocarbons, you needed drop-in substitutes, which turned out to be hydrochlorofluorocarbons. These are shorter lived than CFCs, and so that will be not as harmful to the ozone layer. Then you transition to HFCs, and then eventually all technologies that are good. So we spent a lot of time in our lab testing all these chemicals and showing how bad or how good they were. And it essentially showed there are a lot of good substitutes that could be used. So the first thing that happened was there's things such as propellants kind of got phased out, drop-in substitutes came about, and various other ozone-friendly things happened. And this all happened very quickly and very smoothly. The simplest way I can tell you how successful this was is, how many of you even knew that your refrigerators changed the refrigerants over the years? It was totally transparent to people, and it didn't cost that much or do anything. So it was a very successful transition. And then the HFCs became an issue. Could this be ozone depleting gases? And we showed that it is not, but it is a important greenhouse gas, as I'll show you in a second. So Montreal Protocol is a success. Acceptable substitutes for CFCs were available, and progressively there was elimination of these compounds, very smooth transition, and ODSs are decreasing, and the ozone layer is showing signs of recovery. Now the question is, what else did Montreal Protocol achieve, or what else can it do? While Rowland and Molina showed that the CFCs can destroy the ozone layer, Ramanathan showed that the CFCs were very potent greenhouse gases. That paper was published just 1 year of Molina and Rowland's paper. People had kind of forgotten about it for a little while, but these two phases of the ozone depleting chemicals such as CFCs became a climate issue, and people pointed out that essentially the Montreal Protocol, by taking its action, really did help climate. The simplest message of all these assessments and the papers was, if the warning reduced by the Kyoto Protocol was this little blue bar, what the Montreal Protocol had done was 5 times larger. But the Montreal Protocol was not enacted to help climate, but it helped climate a lot more than other climate treaties. That's a very important point. The actions to protect the ozone layer also benefited climate. Now, it is worthwhile to ask what would have happened if there was no Montreal Protocol. I already showed you this picture of uncertain calculations, projections. This is what's happening in the world now. With 30 years more of scientific knowledge, we can predict what would have happened. I just want you to know that places like India, around here, by now would have seen 25% depletion of ozone above. That would have had a huge impact on agriculture and cataracts and skin cancer in even tropical countries like India. Fortunately, that was avoided. And the question of how the climate change due to ozone layer depletion itself also become important. And these two issues kind of got merged to some extent. Of course, one could ask what could have been done better. And this is the paper where we just showed if people had taken action right when Molina and Rowland came up with their paper. One is about the ozone layer depletion on this side and the climate effects. It would have been really helpful, but it would not have completely eliminated the ozone hole. This is a very important point, and the reason this happens is what are called legacy issues. When you emit chemicals into the atmosphere, they stay so long, even when you start taking action, they don't go away. Same thing is true with carbon dioxide. It lives for centuries. So now, we are living in this phase of the Montreal Protocol, which are called the accountability phase. The way you think about it is, originally you formed this policy for a desired result. You took some action, and now you want to make sure, as this action is being taken, your desired end result is going to come about. So you may have to adapt to this, you may have to change this, but until you get to your desired result, you're never done. Okay? So we already said HFCs are a problem because they're greenhouse gases. This is another set of pictures showing the effect of HFCs, what they would do. This is comparing ODSs with HFCs and how much they could contribute in a metric called radiative forcing, which you can think of as kind of a metric for warming of the earth. HFC is actually comparable and important, and there are some subtle issues that also make them a little bit more important for climate because HFCs do not destroy the ozone layer, and there's a compensation effect by the ozone depleting substances. So the point is, HFCs are a problem. it's not an ozone depleting gas. So should the Montreal Protocol do something about it? So there's a lot of work that is done. And one of the synthesis reports for this was a document that this is Gus Welder, Mario Molina, myself, and Melanie Miller put together, and that showed what needs to be done with HFCs. And this was done, also published in Science afterwards. The key point of this was simple. Look, whatever is done is done. Let's look at what could happen in the future. And what could happen in the future is, if you keep emitting CO2 and look at what happens as the business as usual scenario, and even if you took all the effort to stabilize CO2 at 450 parts per million, if you do not do anything with HFCs, they will completely offset the effort you took to stabilize CO2. So HFCs are going to be counteracting all the actions you take for stabilizing CO2. And there are solutions for this. You don't have to go that way. You can use a different set of chemicals, and that will make life easier. And this is the message from those things. The third message was there are alternatives to even these HFCs. So there's many sectors where you can see there are other alternatives, especially hydrocarbons and not in kind applications for various other things, not just the refrigerants, but for foam, and solvents, etc. And this is the market penetration of these activities. And it shows that it actually is very feasible and it's happening, and you can phase out HFCs. That led to the Kigali Amendment in 2016. This took a while for the countries to agree that the Montreal Protocol, originally made to protect the ozone layer, should also be doing something for climate. The way I look at it is this problem of HFCs came about because of the Montreal Protocol. Montreal Protocol led to phase out of CFCs that made HFCs more common. So you have to kind of own this problem and do something about it. I'm going to skip the rest of the few slides, some of them. This is real chemistry details of one of the things that could happen with the HFCs. And this is about something called trifluoroacetic acid. I'll just tell you in this figure that we have done this calculation for various parts of the world, America, India, China, and Middle East. India is one of the fastest growing markets. The point simply is this production of the toxic chemical from the use of HFCs is hundreds of times less than where it would have toxic effects. And this is how it varies with season. And being in India, this is the monsoon season, which it rains a lot. Okay. Now, at this point, I want to end this talk in the next couple of minutes by asking a simple question. Is Montreal Protocol done? Does Montreal Protocol have any unfinished business, or can it do some more? One of the points I would like to bring up is many years ago, in 2009, we published a paper showing that nitrous oxide was the dominant ozone depleting gas emissions in 2009, and now it has become even more. The point of that was nitrous oxide, people thought of as just natural, but the human produced nitrous oxide is contributing to the ozone layer depletion. And that became the most important ozone layer depleting gas because the CFCs went down. And there are other examples of things like this where there is both natural and man-made sources, and you can focus only on the man-made sources of nitrous oxide. And the biggest component being agriculture and reverse and actually use fertilizers, fossil fuel burning, biomass burning, and atmospheric decomposition. There's actually some industrial activities like production of nylon and things like that. So it's not new that we have a chemical that has both natural and anthropogenic origin that has been controlled. The example I show here is methyl bromide, which is under the Montreal Protocol. So what do we do about nitrous oxide is something to think about. The second thing I wanted to bring up was Steve Monska and company at NOAA in Boulder showed that there is what I would call rogue emissions of CFC-11. CFC-11s were banned, they shouldn't be emitted, but they were being emitted, and it was detectable globally. So this essentially showed that it came from parts of China, and this is where it was happening, and this is kind of the trajectory of it. Once it was pointed out, it has kind of gone down significantly. So we also pointed out there are other chemicals like this in this paper by Susan, Joe Alcomore, and myself in Nature Communication. And there are issues of unexpected increases in chemicals, and how does Montreal Protocol deal with these issues? The way Montreal Protocol deals with emissions is what's called self-reporting. You ask every country to tell how much they're using and how much they're emitting. Do we really know these emissions? How well is that reported? What about chemicals that fall through the cracks? And the point is, science can actually tell what can be done about it. So in this paper, with Ray Weiss, Paul Newman, and myself in Nature, we pointed out that if you look at the places where you can monitor these gases, those are stations shown in these dots, and the footprint over which they can measure these chemicals, the huge amount of the globe is unmonitored. Almost all of Latin America, most of Africa, most of Asia, including India, a lot of Eastern Europe and Australia, etc., are not monitored. And this is something that is really worthwhile doing, and it's cost effective. So in terms of the unfinished business of the 5 decades of ozone layer, I succinctly say that these are 5 steps that the Montreal Protocol can take. It can toughen compliance to make sure that unwanted chemicals are not emitted. But then there is an exception that's used. I didn't have time to go over it. Is the feedstocks. For example, when a chemical is used to make another chemical, that particular parent chemical is not banned, even if though it's ozone depleting gas. A classic example is carbon tetrachloride. Then there are lots of leakages. This is in nobody's benefit to allow leakages, because leakages of chemicals is money being thrown out, and it's bad for the environment. There's something else that could be done. Drying down nitrous oxide is another unfinished business of the Montreal Protocol. Then including monitoring for effective implementation and protecting the ozone layer further through Kigali Plus. You can protect climate even more if you enhance the provisions of Kigali Amendment. I want to stop this talk by just pointing out something very important, since a lot of the audience today is in India. India played a major role in Montreal Protocol. Even though skin cancer was the major kind of concern at that point when it's happened, India is a signatory to the Montreal Protocol and is an active member in many of the amendments and in bringing about these things, especially the Kigali at the end. And India has adhered to the amendments and phased out CFCs ahead of schedule. Secondly, India has shown leadership in this global issue. In fact, one could argue that some of the way India did this and how it used its resources and that of the multilateral fund, etc., is a good model for developing countries. Now, though, India is one of the biggest markets that's emerging for air conditioners and refrigerants. It's going to be skyrocketing, and rightfully so, because people need it. But can that be done environmentally safe ways? That's something that India has to think about. And how can it do it in a green way? And one of the last things for scientific people I would suggest is to really need to monitor and keep track of emissions. And it's better to start now in India with the monitoring, because before things get to be much larger, it'll be nice to have very good baselines. So I want to end this talk on a happy note, on a positive note. When you think about things, it was only 40 years ago that the ozone depleting substance was first predicted to deplete the ozone layer. 30 years ago, roughly, the ozone layer was discovered. Today, it's showing recovery. And even though it's showing a recovery, it will take another 40 years for the ozone layer to recover and roughly 60 years for the health impacts to go away. But it is going to happen. But the point, though, is the world took action to avoid a major disaster. And it actually has been managing this quite well. So that's the lesson for us. So it's a triumph in a way. It went from a postulate to a successful international agreement, and it still can do more. And I just want to end with this cartoon of Gary Larson. It's called The Boson Layer. If you're not into these kinds of cartoons, you may not find it funny. Gary Larson was one of my favorite cartoonists. And just reminding ourselves, we have only one planet and we need to keep it. With that, I thank you for your attention.
Thank you, Dr. Ravishankara, for this exciting and informative talk, because you have been in the thick and thin of the whole policy making, and also as a bridge between the scientists and the policymakers. I think the role that you and your team played, it's very nice to hear and learn about the success of the Montreal protocol and how things evolved. And I'm sure there would be several interesting and questions and queries to discuss further on this. And I will to conduct that, I'll request my colleague Professor Lokesh Sahu to please do the needful. Lokesh, please.
Yeah. Thank you, Professor Raju, and thank you, Professor Ravishankara. It has been always great and to hear you. And today's talk is like a real story. I mean, put together in chronological order, and the key steps, and in overall about the science and policies related to ozone. So as if we are like we are celebrating or observing World Ozone Day. It is like that kind of feeling we are getting here today. So before just I would like to summarize that we have the audiences joined in YouTube as well as in WebEx panel. So first we would request or invite our colleagues who have joined in WebEx panel to interact with Professor Ravishankara about the queries or question or anything, comments, etc. So the openish forum for the colleagues who have joined in WebEx panel. So yeah, please welcome. So you can raise your hand or you can say something. Yeah, so we have Dr. Anup Mahajan from IITM Pune. So, Anup, please go ahead.
Thank you, Lokesh. Thank you for the wonderful talk. It's nice to go through the entire history and see how, as humans, we can be successful if we put our mind to it. You've touched upon the anthropogenic emissions and how they have changed and how we managed to control them. But what I wanted to ask you was, with climate change, there are definite signs that some of the natural emissions of halogen species are also changing. Do you have any comments to make on what effect they would have on stratospheric ozone and whether this is something we need to start worrying about as a secondary effect of climate change, or it's still much further away from the anthropogenic impact?
Thank you for that question. Yes, there are potential consequences of climate change on emissions of halogenated chemicals, especially things that can come from the ocean, things like methyl chloride, methylene chloride, and a few other brominated chemicals, etc. Many of these are short-lived chemicals, but a little. If you add them all up, they can add up to something significant. So right now, it looks like the contribution of those chemicals in today's atmosphere is kind of small, but we should keep an eye on it because it could change, and in which case it could have an effect. Lastly, when you said the climate change could change, I would like to point out nitrous oxide is another molecule we shouldn't forget. It's a big one. It's the third most important greenhouse gas, but it's also a very significant compound in the ozone layer depletion. And that can change significantly in the future climate.
Yeah. So, moving on, so we have Professor Varun Seal from PRL. So, yes.
Thank you, Professor Ravi, for this interesting talk. So my question is related to the nitrous oxide you are telling in some way. Basically, we have seen a very large increase of NOx. So that is NO and NO2 over the Asian and basically China sector. And this has been, in fact, monitored from satellite. So my question is that nitrous oxide is also being monitored. So do you see that this increase is sufficient to destroy ozone?
Okay, you're breaking up a little bit, so let me make sure I understood your question. I think you're asking if NO2 and NO could affect the ozone layer. Not directly. That's an interesting question. And yes, NO2 is one of the, NOx is one of the big pollutants that you can see. NO2 and NO essentially have a very short lifetime in the troposphere of the order of, a day. It will remove quite rapidly, becomes nitric acid and ammonium nitrate, etc. So they themselves do not directly affect the ozone layer. They indirectly affect the ozone layer because they change the chemistry of the troposphere, which then can affect the ozone depleting gases. So it's an indirect effect. So it's what you'd call a feedback. Yeah, that's how, if you change NOx, you can change the pollution levels and the hydroxyl radical concentrations, and that could affect the concentrations of ozone depleting substances, especially those that contain a carbon hydrogen bond.
So just one more question I have. This is regarding when we say the global ozone depletion. So basically, if you look at the polar regions, the polar vortex is a very important ingredient in very high depletion in the polar regions. So should we differentiate that when we say a global ozone depletion?
Yes, you're absolutely correct. The polar ozone depletion is episodic, it's seasonal, and it's constrained. And actually, the chemistry itself is quite different because essentially what happens there is you have a very strong vortex, as you noted, and that prevents very large scale transport across the vortex, and that contains the ozone. And then also because of the cold temperatures, you make polar stratosphere clouds, which starts heterogeneous chemistry. And the chemistry that destroys ozone in the Antarctic ozone hole is things like CLO plus CLO reaction, which are pretty unimportant in the global ozone depletion. And also, the extent of ozone depletion in the vertical is different in the polar versus global. In the polar region, it's almost all lower stratospheric ozone. In the global, it's both lower stratosphere and upper stratospheric ozone. So the structure, temperature, the ozone destruction structure vertically is different.
Thank you, Ravi, for answering the questions. And now we have Professor D. Banerjee from PRN. So I request Professor D. Banerjee to interact with Ravi.
Thank you, Professor Ravishankara, for a very interesting talk and insights into how this major problem was solved. I would like to comment on, the other aspect. I mean, climate change is still an outstanding problem, and greenhouse emissions, have not been controlled as significantly, and we see more and more extreme events of climate in India and elsewhere around the world. So, in your opinion, what needs to be done to, to control the temperature of the Earth, the surface temperature of the Earth, and the emission of CO2, and even this has a political context. I mean, how does one get an agreement, to avert a major crisis in the next 30 to 40 years? Thank you.
You asked $1 million question. I don't know. It depends. Some days I feel optimistic, some days I feel very pessimistic. The one way that I think to go about the climate business is to what I would call nibble away at the climate. If we try to do everything at once, I don't know how successful we'll be. Because honestly, let's be honest. People just don't appreciate the fact that even if you completely stopped emitting CO2, absolutely zero, the world just stopped emitting CO2 today, the climate change is going to get worse before it gets better. Okay? That is usually a message that we don't actually tell people because of various reasons. We can go into the scientific reasons for it if you want. Secondly, people cannot stop because we have to live, we have to cook, we have to move, we have to do. So the ability for us to completely kind of change overnight is impossible. So the idea is maybe we should do things that would help us very quickly. And then while it is helping us, we can take further action. So I'm a very strong proponent of dealing with short-lived climate pollutants immediately. That's one of the reasons I spent a lot of time on methane and the Climate Clean Air Coalition. So if you decrease methane emissions now, you'll kind of decrease the rate of change, and that gives us a little bit more time to do something with carbon dioxide. The third thing I would point out is, God, we better start adapting. Irrespective of what happens, we are going to see climate change. We're already seeing it. and it's going to get worse before it gets better. So we really should be adapting. So the budget for adaptation issues should be very, very significant. It kind of creeps up on you, and it's going to be hard, but it's something that we have to do. That's my thought. I think CO2, things that can be done can have effects. We just did a calculation on what could India gain by essentially switching all its railways to electric rails as opposed to diesel engines. You can gain quite a bit, not only for climate, but also for air pollution. In other words, we really should think about doing things that have multiple benefits, and especially benefits that people can see quickly. If people can see the benefit quickly, they feel like they have accomplished something. If you just tell somebody, don't emit CO2, which you don't see or smell, something is going to be better for your grandchildren, it's very hard to convince people of doing it.
Thank you, Professor Vishnu.
You're welcome.
Yeah. Thank you, Ravi. And moving on, next is Dr. Somkumar Sharma from PR. So, Dr. Som, please.
Thank you, Professor Ravishankara ji, for a wonderful talk. Just the question is, in terms of global warming, there are reports and evidences. There is a signature of a little cooling in the stratosphere and mesospheric regions. So if I take that cooling into account, then how the scenario of ozone will change in coming years? That is my just question.
Good point. As you know, when you increase CO2, the stratosphere has to cool as opposed to the surface. And there's a simple radiative transfer issue. And in fact, the cooling of the stratosphere is the best measured temperature change due to anthropogenic CO2 changes. Okay? You come to a very kind of detailed, interesting, intricate thing. When you change the temperature in the stratosphere, you change the chemistry there to some extent, and that changes the ozone chemistry. So the rate at how ozone recovers, ozone layer depletion changes with time in the changing stratosphere is something that's been discussed quite a bit. The ozone layer in the stratosphere changes both because of the temperature changes due to the greenhouse gases, but also the chemical effects of some of the greenhouse gases, especially nitrous oxide and methane. So it's a complex issue, and there's also a feedback of ozone itself. Ozone is a greenhouse gas. So when you change the ozone, it feeds back on itself in the radiative force, in the radiative, how it interacts with the radiation. So all of those things are done. So the overall effect is when you cool the stratosphere, you get more ozone. Only in the upper stratosphere.
Okay, thank you. That's a good sign.
Except it doesn't completely make up for the depletion.
So, thank you, Ravi. And I guess I had already invited all those who had raised hands. So I don't see any other. So I again invite colleagues, those who have not raised hand, they can ask questions.
Lokesh, there are chat questions.
Okay, so meanwhile, we can go to the chat questions. So the one question is from Nat Gopal Swami. His question is, ozone is also depleted by particles precipitation from the Van Allen belts, the sun, and cosmic rays. What is the relative contribution of these cosmic and human activities to ozone depletion?
Thank you. This is a long-standing question that keeps coming up. The overall effect of cosmic rays and the ozone depletion is negligible compared to that by ozone depleting substances. There are a couple of simple ways to think about it. You know, most of those things, other than when you have solar proton events and things like that, you don't get very far down. And even if it destroys all the ozone that's up there, that amount of ozone is very tiny, because essentially by the time the density is so small. So the overall effect of particles, especially cosmic rays, people have also asked about meteors, is the same thing, is very tiny compared to the human activities. And there are also very clear signatures that show you why we come to that conclusion. Thank you.
So moving on to another question, Ilanganan Agnan. So the question is Johnston's prediction about contributions from supersonic flights for the NO production. Now there is a work on hypersonic flights and missiles. Do these flights contribute less NOx vis-a-vis natural sources?
Yeah, that's a very good question, Arnan. The one thing that happened, unfortunately, I didn't have time to go into this, is the reason the supersonic transport question kind of got dropped is because they got phased out. US never built the supersonic fleet, and the supersonic fleet built by the French-British collaboration is actually pretty minimal. Now, the question of, is there discernible ozone depletion due to missiles and hypersonic flights? That's an interesting question. People have examined, can you see an ozone depletion following a launch of a missile or a space shuttle and things of that nature? Yes, you can. There are discernible signatures, but it's not huge. Now, if you have hypersonic flights again, and depending on the altitude at which it goes, it could have an impact. It's kind of very interesting because the altitude at which the things go hypersonic is very important. If you do it in the lower stratosphere, you deplete ozone. And if you do it in the mid stratosphere, you actually make ozone. It's a complex interaction. I'll be happy to talk to you when I see you in a couple of months.
So thank you. And moving on to next question is from Kumud Pandey. Her question is, are there any other sources that can deplete ozone layer which we have to also consider for future research?
That's a good question. You know, this is the question of unknowns. One of your colleagues just asked about the short-lived chemicals that could be feedback from climate. Those are one things. If you look at the paper that Susan Solomon, Alcamo, and I wrote, we also pointed out there are other chemicals that are routinely used that are not in the Montreal Protocol. These are things like tetrachloroethylene used for dry cleaning and things like that. They're short-lived, but at the same time, even a small fraction of it can, if it gets to the stratosphere, could play an important role. So yes, as long as we focus on catalytic ozone depletion, the only well-known catalysts are nitrogen oxide, halogen oxides, or hydrogen. So that's the second thing to think about. Lastly, if you change the water vapor in the stratosphere, that's going to change the ozone level. Simply Hawks catalyzed ozone destruction.
So thank you. And moving on to next question from Jharna Bora. The question is, are the ozone depleting substances carried from one place to faraway places of the world, just like how aerosols are? Is it significantly affecting the ozone layer in one place due to another? I think if you can make any sense out of this, then.
Okay, I think I know what you're saying. First, if you think about the atmospheric dynamics, how air moves, when you have a compound as long-lived as CFC 11 or 12, it is completely well mixed in the troposphere. And then it goes to the stratosphere mostly via the Brewer-Dobson circulation. There's the going into the tropics, going up, and then coming down towards the polar regions and high latitudes. So the distribution of that is changing with latitude. Not only that, the distribution of the active component also changes with latitude. That's why you have differences in the ozone depletion as a function of latitude. Now, if you're asking about aerosols are actually pretty short-lived compared to the ozone depleting chemicals. Yes, those aerosols are also transported, but they're much, much more inhomogeneous. Aerosols are, much more inhomogeneously distributed in the world.
Thank you, Ravi. So the next question in YouTube is from Mansi Gupta, who is JRF in PRL. Her question is while taking into account global warming potential, are the other quality issues while mitigating, for example, the use of hydrocarbons as low GDP alternative, but at the same time, their ozone farming potentials at much less time scale considered when it is promoted as refrigerant?
Good question. Yes, in fact, whenever these kinds of things are examined, not only do you look at what the global warming potential is for the substitutes, but also ozone formation potential. In general, the amount of ozone formed from the use of something like butane or propane is tiny compared to amount of methane you have in the atmosphere and the other hydrocarbons from trees and transportation, etc. But it is examined though. You have to keep an eye on it to make sure you don't make a problem in a local area that could be bad. Good point.
Thank you, Ravi. And the next question is from Tabish Sari. And his question is, does the surface ozone, which is most harmful for 10 near the surface, also protect us from skin cancer if some UV radiation manages to reach the surface locally?
I don't understand that question, other than
so the question is, what I understand is that we have ozone in troposphere. So if the ozone which can pass through the stratosphere are protecting us.
Oh, got it.
This ozone,
okay. Yes, the ozone increases in the troposphere can offset the ozone depletion in the stratosphere. Absolutely. But the amount of ozone you make in the troposphere is not always sufficient to make up for the ozone depletion in the stratosphere. The other thing that actually affects the UV more than the ozone is the aerosols. The aerosols actually scatter, and that has reduced UV radiation significantly in polluted regions.
Thank you, Ravi. And the next question is from Dr. Narendra Singh from Aris Nainital. This question is, since most of the precursors of ozone may be produced anthropogenically are within 6 to 8 kilometers in the troposphere, particularly over the tropical region, and through body circulation, these gets transported towards the polar regions. Hence, polar stratosphere is affected more. Can we expect such influences in the tropics and mid-latitude regions too?
Yes, I showed a picture. It depends on how much you get. You actually can get ozone depletion in the tropics. You know, the other thing that I did not have time to go through is most of the ozone in the stratosphere is made in the tropical regions. And then it is transported to more and more towards the polar regions. The ozone lifetime and the production rate of ozone varies very significantly with latitude. So if you affect the production region of ozone, you will decrease the ozone going elsewhere also.
Okay. So the next question is from Kamran, who is a PhD student in PRL. And his question is, how much gas leakage contribute to ozone depletion worldwide? Can we detect gas leakages from satellite observations?
Good point. The gas leakage of ozone depleting substances is pretty small and is diffuse in the sense it happens at various places. Okay, so it's kind of hard to detect by satellites. For satellites, especially for the ozone depleting substances, you don't have the contrast. It is not like a methane plume, unless a factory that makes ozone depleting substances all of a sudden, something blew up or something. But these are leaks that happen slowly, and that's hard to detect from satellites.
So
remember, for satellites, for passive satellites, you can do only some. Yeah. Okay, I'm done.
So there's last question from YouTube. The question is simple: how much natural sources contribute to ozone depletion?
That's a tricky question. If it is natural sources, you don't call it depletion. It's essentially happening. It's only when you add something to that natural source do you call it depletion, right? So there's a balance in the amount of ozone that's constantly being produced and constantly being removed. So if it has been happening for a long time and you just consider it your natural background. So depletion specifically refers to what you get, the additional ozone loss that you get when you add an anthropogenic chemical. By definition.
Yeah. So thank you, Rohit, for answering our audiences who have posted their question in YouTube. Now we are coming back to our WebEx colleagues. So we have already one hand raised. It's Professor Neeraj Rastogi. He's from PRL. So Neeraj, please go ahead.
Thank you, Lokesh.
Yeah.
Hello, sir.
Yeah.
First of all, thank you very much for such a informative talk. I was just thinking, means we know that once in a while we used to have very big volcanic eruptions, which put a lot of aerosol and gases both in the stratosphere. So how that affect ozone and how long that effect can be?
It can be very large. Thank you. That's a absolutely fascinating question and area. The aerosols, the volcanic eruptions has a couple of interesting points. One, as you know, it puts out a lot of SO2 and makes a lot of sulfate aerosols in the stratosphere. And the sulfate aerosols provide a venue for various reactions to occur that leads to ozone depletion. So after eruption of El Chichon and Mount Pinatubo, we could very clearly see ozone layer depletion. And you can monitor the aerosol abundance in the stratosphere as a function of time using lidars and things of that nature that you know about. And essentially, the aerosol density in the stratosphere makes a big difference, chemically and radiatively. The second part is there's always a question people wonder about: could the volcanoes themselves put enormous amounts of halogens into the stratosphere? That is been answered to a great extent. It doesn't look like it because a lot of it gets washed out before it gets to the stratosphere. But it's not completely clear to me if some volcanic eruption like a Tambora or one of those enormous Krakatoa or something like that, if that couldn't have put ozone depleting chemicals directly into the stratosphere. But those effects would last, as you know, for about 3, 4, 5 years until the broad Dobson circulation takes them out of the stratosphere.
Thank you, sir. And just let me add one more thing here. So as you have told the successful story of Montreal Protocol for ozone, so is there anything in plan for the surface pollutants, like variety of aerosol and trace gases? They are like slow poison. So since they are slow poison, so people don't worry too much about that.
Yeah. Oh, I work on that. Yes, absolutely. There's a philosophical difference, and that leads to a difference, and that is, what problem is global, and where do you make a treaty and agree, and what problem is local? And air pollution historically has been thought of as a local problem that should be controlled by the local emissions. So there are very few treaties about it. The treaties that do exist are things like LRTAP Convention. It is a long-range transport of pollutants. And there's also some treaties on mercury, Minat, I'm blanking out, Minato or something like that, convention. But for other aerosols, there aren't any conventions, international conventions, but it might be worthwhile thinking about it, especially in a regional sense. So if I were to think about India's air pollution in India, I cannot imagine thinking about it without including the entire Indian subcontinent. Or if you were in Bangladesh, for example, how could you control your air pollution when you're surrounded by India? In fact, Bangladesh air pollution is almost completely influenced by what happens in the Indo-Gangetic Plain. So those kinds of things might be worthwhile for discussion amongst regional countries to come up with air pollution controls. We made a suggestion in one of our papers that a pan-Asia air pollution strategy is probably a very useful tool. I have no idea that it will be done or not.
Thank you, sir. Thank you so much.
You're welcome.
Thank you, Ravi. So, so if there are some questions, then please raise your hands. Otherwise, we are coming towards the conclusion of this Amrut Vyakhyaan session. So it's kind of last opportunity if you have any question. Anybody? So
I've had it for 40 minutes. So
yeah, so still, yeah, thank you very much for that. And but there is a lot of appreciation in YouTube chat box for you. Nice talk. Of course, they don't ask very specific question, but just they say they appreciated your talk. So that
thank
I
you.
thought to convey. So with this, once again, thank you, Professor Ravishankara, for wonderful talk and also, answering questions from our audiences. With this, we are coming towards the end of this Amrut Vyakhyaan session. And in this final step, I would like to invite our colleague, Dr. Bhusit Vaishnaw, for the concluding remarks and a word of thanks. Dr. Bhusit.
Thank you, Dr. Lokesh. Thank you, Professor Ravishankara, for such a wonderful and informative talk, both for scientific community as well as policymakers. And I'm sure that today, when all of us will go home, we have something to take away from the day. Once again, thank you for being there so early in the morning. I think when you started talk, it was 5:30 a.m. at your end. So we are very much thankful to you for agreeing to give talk at such an early hours. Fine. We thank all our YouTube as well as WebEx audience. Today we had close to 260 people who attended this talk live, and I'm sure that many more will watch it on YouTube as the time passes. We are thankful to our director and dean for their time to time guidance and support for carrying out this Vyakhyaan activity so nicely. I'm thankful to the committee members of this Vyakhyaan activity, especially the chair and co-chair, for always being there to support various activities and announcements for this Vyakhyaan. We thank all those who have joined today and will be joining in future and have joined us in the past. Next week again we'll be back with another interesting Vyakhyaan at same time 4 p.m. Please join with us. And until then, take care and good night. Thank you, sir.
Thank you. Bye now.
Bye.
Thank you.